Hello children, I am very happy to stand in front of you to teach physics through online. Today's topics are belongs to the unit 3, that means magnetism. Let us go to the class now. Today's first topic, Coulomb's inverse square law of magnetism. Children, listen the lesson very clearly. Ask doubt if you feel not understand. Consider two bar magnets A and B as shown in the diagram. When the north pole of the magnet A and the north pole of the magnet B or south pole of the magnet A and the south pole of the magnet B are brought closer, they repel each other. On the other hand, when the north pole of magnet A and the south pole of the magnet B or south pole of the magnet A and the north pole of the magnet B are brought closer, their poles are attract each other. This looks similarly to Coulomb's law for static charges studied. So, we should understand that same poles are repelled, opposite poles are attracted. You can understand very clearly from this picture. Now, in unit 1, now opposite charges are attracted. You don't understand that. So, analogous, same, analogous meaning is same. Coulomb's law in electrostatics. We can state the Coulomb's law for magnetism. How can we define Coulomb's law in magnetism? Can define with help of this diagram. What is that? See, it is 2-mark question. Define Coulomb's law in magnetism. That's the question. The force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strength and inversely proportional to the square of the distance between them. Enough. 2-mark. Mathematically, we can write F vector directly proportional to the QMA QMB by R square into R cap. Here QM means pole strength of magnet A, QMB pole strength of magnet B. R square means square of the distance between the two magnets. R cap means direction of the magnet from one magnet to the another magnet. Clearly explained. So here we should allow K. K is the constant where we place these two magnets in the air medium or water medium or glass medium with respect to it. In magnitude, it can be written like this. F vector is equal to K QMA into QMB by R square. Now, the SI unit of the value of K for free space is mu naught by 4 pi, its value 10 power minus 7 Henry per meter, where mu naught is the absolute permeability of free space or air medium. That means how much amount of magnetic lines of force allows or allowed by air medium. That is the meaning permeability. Solve the problem. 3.5. We move directly to the next topic. What is the next topic? Magnetic field at a point along the axial line of the magnetic dipole. or bar magnet. Very important. 5 more question. Consider a bar magnet NS shown in the diagram. Let N be the north pole and S be the south pole of the bar magnet. Each of pole strength Qm and separated by a distance of 2L. The magnetic field at a point C lies along the axis of the magnet at a distance from the geometrical center O of the bar magnet can be computed by keeping unit north pole. That means pole strength is equal to 1 ampere meter at C. The force experienced by the unit north pole at C due to pole strength can be computed using Coulomb's law of magnetism as follows. It is same as that of electric field at a point C due to positive charge. We already studied in lesson number 1 like that. The force of repulsion between the north pole of the bar magnet and the unit north pole at point C in free space is F vector n is equal to mu naught by 4 pi Q m by r minus L whole square into I cap, where r minus L is the distance between north pole of the bar magnet and the unit north pole at C. The force of attraction between south pole and unit north pole at point C in free space is Fs vector is equal to minus mu naught by 4 pi Qm by r plus L the whole square r cap. R plus L is the distance between the south pole of the bar magnet and the unit north pole at point C. Likewise, we have to follow. This is the diagram of this topic. Just to go through the diagram very clearly. Now, from the derivatives 3.9 and 3.10, the net force at point C is F vector is equal to force due to north pole plus force due to south pole. From the definition, definition means from Coulomb's law of magnetism, the total or net force is magnetic field due to magnetic dipole at a point C is, we should add this both derivatives. Finally, we will take out the common values from these two derivatives. We will get, I think that you can understand. Finally, you can get B vector is equal to 3.11 derivative. Children understand? I hope you that you understand. Since magnitude of magnetic dipole moment is P vector modulus is equal to Pm is equal to Qm into 2L. What is mean by Pm dipole moment? The magnetic field at point C, equation 3.1 can be written as 3.11 can be written as, that means magnetic field axial line mu naught by 4 pi 2r Pm by r square minus L square whole square at I cap. If the distance between the two poles in a bar magnet are small, looks like short magnet compared to the distance between the geometrical of bar magnet and the location point C, that means R is very greater than L. So L can be neglected. L can be neglected. Simply R square minus L square the whole square nearly is equal to R power 4. That is the derivative 3.13. Therefore, using equation 3.13 in equation 3.12 we get B axial is equal to mu naught by 4 pi 2 Pm by R cube I cap. mu naught by 4 pi 2 by r cube p vector m, where p vector m is equal to pm I cap. Finally, we will get derivative 3.14. Next, magnetic field at a point along the equator line due to magnetic dipole. That means magnetic dipole at a point on the equator line due to bar magnet. Same as that of lesson number 1, where we studied electric field at point C at the equator line due to dipole. Consider a bar magnet Ns given in the diagram. Let N be the north pole and S be the south pole of the bar magnet, each with pole strength Qm and separated by the distance of 2L. The magnetic field at a point C lies along the equator line at a distance r from the geometrical center O of the bar magnet can be computed by keeping it unit north pole 1 ampere meter at C. The force experienced by the unit north pole at C due to pole strength north-south can be computed using Coulomb's law of magnetism as follow. We'll write like this. See the diagram very clearly. See the diagram. Draw the diagram when you study this question and take practice. So therefore, the force of repulsion between the north pole of the bar magnet and the unit north pole at the point C in free space is, we can get the derivative 3.15, where Fn is equal to mu naught by 4 pi Qm by r dash square. The force of attraction in free space between the south pole of the bar magnet and the unit north pole at the point C is, see the diagram, components of force opposite sin theta, positive sin theta, negative sin theta, cos theta, like that. Finally, you will get derivative 3.16. Go through it clearly. I hope you that you are mathematics students. It's very easy. So force of south pole mu naught by 4 pi Qm by r dash square. Now we have to add both the derivatives. So v vector which is given. So since force due to north pole is equal to force due to south pole, we got derivative 3.17. In a right angle triangle NOC, so in the diagram 3.17, cos theta is equal to adjacent by hypotenuse. That means 1 by r dash. So we have to substitute this 3.18. That is 1 by r square plus l square whole 1 by 2. Substituting equation 3.1 and derivative 3.17. Finally, we will get the derivative 3.19 minus mu naught by 4 by Qm 2L by r square plus l square whole 3 by 2 I cap. Children, again and again I am telling that I am just go through that. That means I am just telling the derivative number. You should study this question by using study materials or using rough note. Since the magnitude of magnetic dipole moment is Qm into 2L, substituting 3.9, the magnetic field at point C is V equatorial is equal to minus mu naught by 4 by Pm by r square plus l square whole power 3 by 2 I cap. The same as that of if the distance between the two poles in a bar magnet or small, looks like short magnet when compared to the distance between geometrical center of bar magnet and the location point C is, that means r is very, very greater than L. We move, that is we move derivative number r square plus l square whole 3 by 2 is equal to r cube in mathematically. Using equation 3.21 in equation 3.20, b equatorial minus mu naught by 4 by pm by r cube I cap. So here pm I cap is equal to pm vector. In general, the magnetic field at the equatorial point is given by b equatorial is equal to minus mu naught by 4 by p vector m by r cube. Note that magnitude of b axial is twice that of magnitude of b, and the direction b axial and b equatorial are opposite. Try to solve the problem 3.6, get more knowledge. Try to train yourself for NEET or IIT like that courses. Now go through the topic. Next topic is torque acting on a bar magnet in uniform magnetic field. Consider a bar magnet of length 2L, pole strength Q is kept in the uniform magnetic field. Each pole experiences a force of magnitude QMB but action in opposite direction. Therefore, the net force exerted on the magnet is 0, so that there is no translatory motion. These two forces constituted a couple about the midpoint of bar magnet, which will rotate and try to align in the direction of the magnetic field B vector. So therefore, force experienced by the north pole F vector n is equal to QMB vector. The force experienced by south pole, which is given minus QMB vector. Adding these two derivatives, we will get total force is equal to 0 vector. Then see the diagram. The magnet is placed on the magnetic field is in this form. I think that maybe problem and 3 more question, and also 1 more question can be arised from this topic. This implies that the net force acting on the dipole is 0, but forms a couple which tends to rotate the bar magnet clockwise in order to align it along B vector. The moment of force or torque experienced by north and south pole about point O is torque vector is equal to On vector into Fn vector plus Os vector into Fs vector. Torque tau is equal to On vector into QMB vector plus Os vector into bracket of minus QMB vector. By using right hand corkscrew rule you studied in 11th standard. So conclude that total torque is pointing into the paper. Since magnitudes On vector is equal to Os vector is equal to length of the bar magnet, modulus of QMB vector is equal to modulus of minus QMB vector. The magnitude of total torque about point O we got like this derivative, and finally derivative number 3.25. Go through it and take practices. And torque tau Pm B sin theta. Solve the derivative 3.7 and we move the next. Potential energy of bar magnet in a uniform magnetic field. See that there is a uniform magnetic field on which a bar magnet having north and south pole is placed, which is same as given in the diagram. When a bar magnet magnetic dipole of dipole moment P vector M is held at an angle theta with the direction of a uniform magnetic field B vector. The magnet of torque acting on the dipole is modulus of tau vector is equal to P vector into B vector sin theta. When the dipole is rotated through a very small angular displacement d theta against the torque tau at a constant angular velocity, then the work done by extended torque for the small angular displacement is given by dw is equal to modulus of tau external into d theta. The bar magnet has to be moved at a constant angular velocity, which implies that modulus of tau vector is equal to modulus of tau external. Finally, we will get the small amount of work done by the magnetic field Pm b sin theta into d theta. The total work done is rotating the dipole from theta dash to theta is, see that this is the, finally we will get W is equal to minus Pmb cos theta minus cos theta dash. So the work done is stored as potential energy in a bar magnet and angle theta when it is rotated from theta dash to theta, and it can be written as U is the potential energy minus Pmb cos theta minus cos theta dash. In fact, the equation 3.26 gives the difference in potential energy but between the angular position from theta dash to theta. We can choose the reference point. Theta dash is equal to 90 degree, and so the second term in the equation becomes 0, and the equation 3.26 can be written as U is equal to minus Pmb cos theta 3.27. The potential stored in the bar magnet in a uniform magnetic field is given by U is equal to minus P vector into B vector 3.28. One more question, case 1. Go through it. And point 1, point 2. So we can infer from the above two results the potential energy of a bar magnet is minimum when it is aligned along the external magnetic field, and maximum when the bar magnet is aligned anti-parallel to the external magnetic field. Thank you, children. Go through the exam 3.8. If you feel any doubt, ask me through message or by calling WhatsApp call or by calling video call or by simply normal call. Thank you very much. We will see next class.